The amazing physics of Mars 2020 Perseverance, EDL. After almost 7 months of travel to Mars, the Perseverance lander has to transition from an interplanetary projectile traveling at over 40 kilometers per second relative to its launch point to a functioning science lab and mobile outpost on the surface of Mars. In doing so, the technology aboard the vehicle and the rover, some new and some already developed, needs to perform flawlessly the first time. Otherwise, it's game over. Some amazing physics takes place in the execution of the mission, from choosing the launch date and window, the orbit and trajectory, which we describe and cover in the previous video. That's otherwise hasn't even started yet. Welcome, friends. This is Dr. Jim Daly of Astronomy for Change here, your host, to bring you along on another amazing venture in physics, from the launch of Mars 2020 Perseverance to the surface of the red planet. The EDL phase starts with stabilizing the incoming 5.3 kilometer per second projectile as it hits the thin, tenuous Martian upper atmosphere for the first time without angle or path has been established, to the precision choreography of ejection of the heat shield, parachute deployment, and activation of the descent stage to the sky crane maneuver. All has to proceed flawlessly the first time from the top of the Martian atmosphere to the surface. 7 minutes before landing, and at an altitude of 130 kilometers, Perseverance slams into the Martian atmosphere at almost 20,000 kilometers per hour, or 5.3 kilometers per second. Air can't get out of the capsule's way rapidly enough or fast enough, so a shock forms that compresses the oncoming gas in front of it. The execution of this phase of the mission, the entry, descent, and landing, or EDL, is probably the most difficult, since once the rover is on the surface, there is less pressure and more options available to address any contingency should it arise. The situation is ironic as it is challenging and difficult in that the entire package has to perform autonomously without any intervention. Mission controllers are powerless to intervene, hence the term 7 minutes of terror, the scenario, and only one possible outcome for the mission. When the vehicle arrives at Mars, and within the space of 7 minutes, the technology and the physics kicks into high gear, starting with the heat shield slamming into the Martian upper atmosphere at over 5.3 kilometers per second. The heat shield at Jezero crater, using the vehicle's onboard thrusters, rapidly firing them as necessary. As the vehicle's heat shield hits the upper atmosphere, 190 kilometers above the surface, the amazing choreography plays out in perfect cadence along the 800-kilometer-long path to Jezero crater. Kinetic energy, the energy of motion, varies as the second power of the velocity, so any change in velocity will result in and play a significant role in the vehicle's trajectory, behavior, and mission outcome. With a mass of not less than 3,000 kilograms, the mass of a small to mid-sized car, and a speed of 5.3 kilometers or 5,300 meters per second, the vehicle's kinetic energy is 13.3 gigajoules, an energy that is instantly converted to heat energy as it slams into the Martian atmosphere with a braking force of 62,000 pounds, a reverse braking force of 62,000 pounds. The vehicle anticipating its forward momentum in preparation for the next step in the sequence. This intense aerodynamic braking momentarily heats the thin Martian atmosphere to temperatures approaching that of the surface of the Sun, transforming the rarefied gas into a plasma. And we can hear mission controllers often discussing this, using this terminology. The vehicle quickly slows to subsonic velocities in less than 3 minutes as the energy bleeds off. Within a period of less than 30 seconds, the vehicle slows from over 5,300 meters per second to half the speed, and note how the velocity continues to decrease as we look at this illustration. The spike in temperature here represents the moment the vehicle slams into the atmosphere at its interplanetary cruising speed in the last leg of its trip of 55.3 kilometers per second, with a secondary spike representing additional loss of kinetic energy the moment the parachute is deployed. Forward kinetic energy is converted to heat energy by the back shell and heat shield, resulting in maximum aerodynamic braking 30 seconds after atmospheric immersion at an altitude of 20 kilometers above the surface. This aerodynamic braking is the result of frictional heating between the heat shield slamming into the Martian atmosphere at 5.3 kilometers per second, much the same as a meteor, and is the reason why we see on Earth we see meteorites as simply meteors, which are bits of debris left over from comets that have passed by in the Earth's orbit. As the Earth plows through this debris field, the meteors then, basically there's a relative velocity of the Earth's orbital velocity of 29.8 kilometers per second into the Earth's atmosphere. That tremendous heat, that tremendous velocity causes the meteor through frictional heating to disintegrate. Most of them disintegrate before they reach the surface. If they do reach the surface, they're called meteorites, just as an aside. The resulting opposing force against the Perseverance vehicle as it careens through the Martian atmosphere at high altitude is a force of 62,000 pounds of resistance, and causing a reverse acceleration of 10 Gs. That causes the vehicle to slow from 5.3 kilometers per second to 3 kilometers per second within 30 seconds. The final and most critical leg of Perseverance's journey to Jezero crater plays out in a precisely choreographed sequence of events over the next 7 minutes. As the vehicle encounters the Martian atmosphere for the first time at 190 kilometers altitude, the final 800-kilometer long leg of the journey begins. 43 seconds later, the entry interface point is marked at an altitude of 119 kilometers, with the vehicle traveling at 5.3 kilometers per second. Another 56 seconds later, at 99 seconds, atmospheric immersion begins at an altitude of 63 kilometers above the Martian surface, with the vehicle still traveling at the cruise velocity of 5.3 kilometers per second. And here we see a diagram illustrating the velocity, the acceleration. Here's maximum aerodynamic braking. We can see here's the initial velocity, and it basically is reduced to almost half within the space of 30 seconds. We have indicated here atmospheric immersion, temperature, the heating of the back shell, 878 degrees, the instant it touches the atmosphere. And as it continues to careen through with maximum aerodynamic braking here, these are instantaneous temperatures, and it's not a sustained temperature. That's 6,000 degrees Kelvin. That's the surface temperature of the sun. That's instantly dissipated as the vehicle slows down. And there's a time average temperature of about 1,700 degrees. Here we see at the bottom of this chart here. Down here. Parachute deployment, we can see here there's another slowing down as it continues. Heat shield separation occurs here. To focus the point even more about the dissipation of heat energy and how much energy that involves, the 940 megawatts of power dissipated as kinetic energy converted to heat energy during that 30-second interval exceeds the power produced by many power stations in the 1 gigawatt range. In fact, the total energy in watt hours dissipated in the 5 minutes between 190-kilometer altitude as the vehicle approached the entry interface to the point immediately after the heat shield separates from the vehicle at an altitude of 9 kilometers was 244 megawatt hours, or enough energy to power 1,220 standard homes for 1 month, with an average consumption of 200 kilowatt hours per month, which is the standard consumption for a residential dwelling. And here we can see this right here. Total watt hours, 244 megawatt hours, right here. Kinetic energy is converted to heat energy by frictional heating Atmospheric re-entry is always fraught with danger, especially in a situation when the vehicle is flying by autopilot, which was the case with Perseverance and all these Mars rovers. The Perseverance aeroshell is, quite literally, a controlled meteor in every sense of the word. The rapid conversion of forward kinetic energy to heat energy by the heat shield results in intense aerodynamic braking, momentarily heating the thin Martian atmosphere to temperatures approaching the photospheric temperature of the Sun, transforming the rarefied gas into a plasma. And we saw it previously that the time average temperature was about 1700 degrees. And when the heat shield is that was protecting the rover, which was all nestled inside, protected from the harsh extreme environment just outside. Here we see the diagram, atmospheric immersion, the force. This is in newtons. This is the force in pounds. Just as the vehicle touches the Martian atmosphere. Okay, and this is the power in watts. That's 423,000 watts at that point. Maximum aerodynamic braking occurs here, and here we have a force of 273,000 newtons, or 62,000 pounds of force right here. How much work, or the amount of energy required that was applied to slow the vehicle down is seen right here. 25 billion joules, 25 gigajoules. The power right here, 940 megawatts, causing an elevated temperature, an instantaneous temperature of over 6,000 Kelvin, which is the photospheric temperature of the Sun. As the vehicle slows down, these values will decrease, as we see here. The vehicle quickly slows to subsonic velocities in less than 3 minutes as the energy bleeds off, and we can see that depicted in this illustration here. This is temperature, the vertical axis, and velocity in the horizontal axis. Okay, here we see a constant temperature as the vehicle slows down from 5,000 to 4,000 meters per second. Here's 3,000 meters per second. Here's where we have maximum aerodynamic braking, right here, and the highest temperature. Within a period of less than 30 seconds, the vehicle slows from over 5,300 meters per second. Note in the diagram how the velocity continues to decrease as we look at the illustration. Okay, the velocity is getting smaller as we move to the right. Okay, and the temperature is decreasing, which is consistent with what's happening. As the vehicle slows down, there is less and less frictional heating, resulting in a lowering of the temperature. So how do we calculate the temperature exactly? And this is all standard physics. The frictional heating of the heat shield results in a time averaged energy loss and rise in temperature of almost 1700 degrees, with a total power dissipation of 244 megawatts during these 30 seconds. The same power produced by a small to intermediate sized power plant in an hour. So how do we calculate that? The Stefan-Boltzmann power law. Power, the time rate of change of energy, is the area times sigma, which is the Stefan-Boltzmann constant, times temperature to the fourth power. So the power varies as the fourth power of the temperature. And we can see how as the temperature changes very slightly or a little bit, this would be a tremendous change in power. Okay, the area is the area of the heat shield, which is simply given by pi r squared, where r is the radius of the heat shield, which is about 2 meters. Sigma is the Stefan-Boltzmann constant, and temperature. The temperature is our unknown quantity. Solving this expression for the temperature, we get the following. The temperature is the fourth root of the power divided by the area times the Stefan-Boltzmann constant. Each of the temperature cells in this column are populated with this formula using data, input, and calculations from previous cells. That's how we did this. And much of this data Much of these calculations were based on real live data by live data and telemetry from NASA and JPL as the vehicle proceeded through the atmosphere. Now here we see the initial atmospheric immersion, slight rise in temperature of just less than 900 degrees, right here. Now, the temperature remains constant until the aerodynamic braking really starts to kick in. And here, we have maximum aerodynamic braking here. And the heat quickly dissipates. Now these are instantaneous values, and that quickly bleeds off and is dissipated very quickly. And it's a time average result here at the bottom of about 1700 degrees. We can see as the power in watts and the temperature vary as the vehicle plunges or careens through the thin Martian atmosphere. That's why we see up here the atmosphere is still very thin and rarefied, so there's not much change. But as it gets further and further into the Martian atmosphere, the aerodynamic braking really starts to kick in and the vehicle slows down. Down here at the bottom, this is the second spike that represents the parachute deployment. Okay, you notice here that the vehicle is slowed down to only about 200 meters per second at this point. The horizontal axis indicates velocity. Down here, here's 1,000 or 1 kilometer per second. Down here, it's like 200 meters per second. So the vehicle, this is where we deploy the parachute, and you can notice, rather than temperature, this illustrates more the dramatic slowing down or deceleration of the vehicle as the atmosphere thickens. Within a period of less than 30 seconds, the vehicle slows from over 5,300 meters per second to half that speed, and we note how the velocity continues to decrease looking at this illustration. Spike in temperature here represents the moment the vehicle slams into the atmosphere at its interplanetary cruising speed, or the upper atmosphere. It just touches the Martian atmosphere here, and as the atmosphere thickens, this is where we see the maximum aerodynamic braking here. Within the secondary spike, as we explained, resulting in additional loss of kinetic energy the moment the parachute is deployed. As stated, these calculations are based on real-life data, real data, and telemetry obtained through NASA and JPL. It's interesting to see how the EDL dynamics played out graphically, something we astrophysicists generally are interested in observing, as it better helps our understanding and insight. As expected, we observe the constant temperature with decreasing velocity, while the vehicle is still at high altitude, and then punctuated by the sharp temperature spike at the point of atmospheric immersion and maximum aerodynamic braking, followed then by the rapid decrease in temperature with velocity as the vehicle proceeds through the ever-thickening Martian atmosphere. With only 5 minutes in space left, the rover will drop two 70-kilogram or 154-pound weights to lighten its load. As the spacecraft enters the Martian atmosphere, the drag produced drastically slows it down. But these forces also heat it up dramatically. Peak heating occurs about 80 seconds after atmospheric entry. Additional new technology includes the Ingenuity helicopter to be deployed over the coming weeks, and the sample collection system, a system that will autonomously sample the surface, place the samples in sterile containers, and leave them on the surface for retrieval by a future mission to be launched in about 4 years. Many of the quantities and values presented in this video are the result of calculations performed by myself and others here at Astronomy for Change from real data and telemetry obtained from NASA and JPL. This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. And remember, the Earth is a mote of dust floating in a sunbeam. That's reality. Everything else is just marketing. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect a positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and choose a membership level suitable for you. Every little bit helps produce the great content and further our mission. Also, why not consider becoming a member? Choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.